All right, so Unit 1, Lesson 3, we're looking at one-to-one functions and inverse functions. And so yesterday, or previously, we looked at two activities that involved creating the graph of an inverse. So what we did was we took a function y equals 2x plus 3, which is kind of graphed there in bold. And what we did to create the graph of the inverse was we folded this graph. We reflected the graph of the function across the line y equals x. We transferred the image, and then we ended up with this graph. Okay, so we said that the relationship between inverses is that they are symmetric with respect to y equals x. All right, so there's the second function, y equals x squared. One of the things that I didn't do is I didn't label this as y inverse. Remember, this is the little notation for inverse. Not sure who came up with that, but that's okay. So now what I want us to do is I want us to take a look at Lesson 3 and kind of summarize and what we talked about yesterday, which is what we just did, and then extend the learning to more information about inverses. So here where's my ruler? Here's my ruler. Here is the equation, or here's the graph of y equals 2x plus 3. That's what we started with yesterday. So do these two graphs represent inverses? And the answer is yes, because there is symmetry with respect to y equals x. So these two graphs are inverses. Now what I want us to do is I want us to look at these two graphs individually. Taking a look at our original y equals 2x plus 3, this being the graph, does this graph represent a function? And it does. How do we know that? It passes what test? It passes the vertical line test. So is this graph a function? And the answer is, yes. Well, what about its inverse? What about its inverse? Is the inverse of this function also a function? Yes. Okay, then let's take a look at the second example that we worked with yesterday. We had a quadratic, y equals x squared, which is that right there. Does this graph represent a function? In other words, does this pass the vertical line test? And the answer is yes. So this is also a function. What about its inverse? So if the graph of its inverse does not represent a function, so the answer to this question is no. The inverse of this function is not an inverse, and that's okay. What that tells us is that not all inverses of functions are functions themselves. So the original was a function, but its inverse is not. If an inverse of a function is also a function, then we say that the function is one-to-one. Ooh, there's a lot of the word function is used a bunch of times there. Okay, so let's put this back in perspective. So going back to our two examples, this function, this graph is a function. Is its inverse a function? Yes. So what that means is that y equals 2x plus 3 is a one-to-one function. What about this one? This particular graph is a function, but is it a one-to-one function? No. this is not a 1-to-1 function. So the question is there something that we could do? Is there anything that we could do to determine if the functions are 1-to-1? Let's think about this one. I want to know if f of x equals x cubed is a 1-to-1 function. In other words, I want to know, is its inverse also a function? Well, let's think about what that graph looks like. So f of x equals x to the third. Its graph looks like this. It's x cubed looks like this. And so the answer to this question is yes, this graph is this function is a 1-to-1 function. Let me put another example up there. Let me just kind of sketch another one. What about this one? What if I have the graph of, that's a pretty bad graph, however. Does this graph represent a function? Yes, it passes the vertical line test. This graph, however, is not 1-to-1. This function is not 1-to-1, which means its inverse is not a function. But the question is how do I know that? How can I determine that from the graph? I didn't do any math on it. Some of you may be kind of like turning your head to see if you can figure out if it's, if it has the symmetry with respect to the mom and daddy line. But I'm just going to go ahead and tell you, and this is where, this is the one part of the flipping business that I don't really like, because I would want you guys to kind of play around with this. I don't like to tell you things, but I'm going to have to tell you. Not only is there a vertical line test, there is also a horizontal line test. So, does this graph pass the horizontal line test? And it does not. So, this graph does not pass a horizontal line test. This graph does. Notice that this graph does not pass a horizontal line test, and this graph does. So when a function passes the horizontal line test, that means that this function is 1-to-1, which means its inverse will be a function. So here, since this graph, this function does not pass the horizontal line test, that tells us that its inverse is not a function. And we can see that graphically here. All right, and then for this one, this particular cubic function passes the horizontal line test. So this graph would be a 1-to-1 function. Specifically, what would the graph of its inverse look like? It would look like this. Now, you don't necessarily have to know that, but if you were to, produce the image by reflecting the graph, that's what it would look like. And this graph does not pass the horizontal line test. It is a function, but it's not a 1-to-1 function because it does not pass the horizontal line test. Okay, so we know the relationship between a function and its inverse. We know that there has to be symmetry with respect to y equals x. We know that some functions are 1-to-1 and some are not. Now let's talk about, what if we have an equation of a function and we want to find the inverse? Okay, well, if f of x equals x squared, and I want to find this is saying find the inverse of f. Find the equation for the inverse of this function. And that is f inverse of x. So the question is how do we go about finding the equation for an inverse? Well, here's what I want us to do. I want us to go back to, you can either go here or you can look at your patty paper. It doesn't matter. But here's what I want us to do. I'm going to pull this one out. I want to identify, if you notice that you have a point, let's see, I don't know that this will write on it, but this point, no, it will not. This point is 1, 2, 0, 3. This point would be, let's see, 2 over 1. So that would be point 2, 5, sorry. I just drew a blank there. Okay, so now let's talk about, how about this point? This is what, -2, -1? So let's talk about this. If you look at 0, -3, not 0, -3, is 0, 3 a point on its inverse? No. But how about this point? What is this point? This point is 3, 0. Well, what about 2, 5? Well, if you look at the inverse, 1, 2, 3, 4, 5, this point is 5, 2. And then if you look at the point -2, -1, what point do you think would be on its inverse? Well, -1, -2, which is this point right here. So graphically, we know that inverses have symmetry about the line y equals x. Well, what's the relationship between the points of inverses? Well, look at the points that we just kind of identified. What's the relationship between these points? Well, the relationship is if xy is a point on one, then yx is a point on its inverse. So there's another characteristic of inverses. So now going back to the question, what is the equation for the inverse? Well, the biggest relationship between points is the fact that the x's and the y's are flipped or switched. So if you look at f of x equals x squared, you may be saying, well, I don't see a y. Well, yes, you do. This is the same thing as y equals x squared. To find the equation for an inverse, switch the x and the y. So this becomes x equals y squared. Now solve the equation for y. How do you find, or how do you undo the square on the y? Take the square root of both sides. And this turns out to be y equals, now remember, it's not just the square root of x, it's positive and negative square root of x. Because remember, when you take the square root, when you put the square root into the problem, that's when it's positive and negative. So here we have y equals positive and negative the square root of x. So how do you indicate the inverse? Well, you indicate it with a little -1. But there's an issue with this. This does not represent a function, because remember what the graph of the inverse looked like? It looked like this. Well, I can't, what I'm going to do is I'm just going to restrict the graph of this to where my x's have to be greater than 0. Okay, I don't want you to worry so much about this, but what I do want is I want us to be able to write the equation for the inverse of this function for all of the x's that are greater than 0, and that will be f inverse of x equals the positive square root of x. So if I restrict the domain for this, all we're going to see is that portion of the graph. Yep. Okay. So how do you find the equation? How do you find the equation for an inverse? You switch x and y. Here we will make this an x. I'm going to come over here. And the x becomes y. And you solve this equation for y. So first thing I'm going to do here is after I've switched my x and the y, I'll subtract 6. So x minus 6 equals 1/2 y. And now I will multiply the entire equation. To get rid of the 1/2, I'll multiply by 2. And that gives me 2x minus 12 equals y. And to indicate that this is the inverse, if you also think about what the graph of this is a line. You know it's a function. Then the equation f inverse of x is equal to 2x minus 12. Now, what can you do to verify that those two are inverses? Well, if you graph both of these, then you should see symmetry with respect to y equals x. So I'll pull this out, and I'm going to clear out everything that I have in my y equals. For y1, I'm going to put the original f of x equals 1/2 x. I'll even just use 0.5x plus 6. And I will go to y2 and type in 2x minus 12. I'm going to have the calculator graph this on a standard window, so I'm going to choose zoom, and number 6 is standard, and what that means is the calculator will graph it on a -10 to 10 window. And here comes the graph. I'm sorry, this is kind of hard to see for some reason. Let me see if I can't scoot that up. I'm not really sure. There we go. So I know this is a bad, let me try something. Okay, so either way, does the graph of these two functions, is there symmetry with respect to y equals x? And the answer is yes. I can verify. I'm not really sure. Okay, how can I? Okay, I'm not sure how to do this. I will work on this before next time. But I can always verify some things. If I press trace right here, notice that I get the cursor on 0.6. 0.6. If 0.6 is on this graph, what should be on its inverse? 6.0. So if I use my down arrow key right here or my up arrow key, either one, notice, well, it didn't. Notice that my cursor, is no longer here. It's on the second graph, which is red, and you can see that it's at 0, -12. So if I type in 6 for x and then enter, notice that the calculator will put the point at 6.0, which indicates one point that verifies that these two graphs are inverses. Okay? All right. So now let's kind of wrap this up a little bit, and let's pull in another aspect of inverses. So the last thing I want us to do here is well, it's not the last thing. I've got one more thing after this, but I want us to show that the following pairs of equations are inverses. And this wording, show, is a pretty big word because there's a lot that has to happen for you to show that these two equations are inverses. So we're going back to lesson 2. We kind of have to rely back on lesson 2 with composite functions. to show that these two are inverses, I'm going to take the f inverse and put it into the f function, and then I'm going to take the f function and put it into its inverse. So what does that look like? In the original function, which is 1/2 x plus 6, I'm going to substitute f inverse, which is 2x minus 12. Okay, so f of 2x minus 12, f of 2x minus 12 is equal to, now let's see what happens when we distribute. 1/2 times 2 is x. 1/2 times 2x is x. And 1/2 times 12 is 6, so that's x minus 6 plus 6, and that cleans up to be x. Okay, so we're only halfway through showing that these two equations are inverses. Now what we have to do is we have to take and evaluate the inverse function to x minus 12, and I have to evaluate it at the f function, which is the 1/2 x plus 6. So everywhere I have an x, I'm going to substitute it for x, and now I'm going to simplify this expression. So this turns out to be, if I distribute the 2 onto 1/2 x, I get x. 2 times the 6 is 12. When I subtract 12, I'm left with x. Now, what you've just done, or what we've done, is we have shown that these two equations, or these two functions, are, in fact, inverses. Now, what about this process indicates that they are? Or what is it that proves that they are? Well, there's 2 steps to this. Like I said, you have to take the inverse and put it into the original, which is what we did here. And then you have to turn around and take the original and put it into the inverse, which is what we did here. What's showing that they are inverses is the fact that they both reduced down to x. And there's some significance to the fact that they're both x. And I'm wondering if you can determine what the significance is. It has to do with the symmetry. Remember, what is the relationship between the graphs of inverses? The graphs are symmetric with respect to y equals x. That is the significance. So, showing that these two equations are inverses, what we have is that the function evaluated at its inverse of x is the same thing as the inverse evaluated at f, and they both equal x. So this is your statement that those two equations, those two functions are inverses, and you're explaining why they are inverses. When you substitute each into the other, they should always simplify down to x. Now, if they simplify down, it's not because they simplify down to be the same thing. The same thing has to be x, and it has to do with the symmetry that characterizes inverses. All right, so what about this one? Okay, I want us to show that g of x equals x cubed and g inverse of x, which is the cube root of x, are inverses. And it's as simple as evaluating each function in terms of its other. So we'll start g of the cube root of x will equal, take the cube root of x, put it in for x, and now cube it. What's going to happen what happens when you cube a cube root? They just cancel each other, and you're left with x. okay? Then you have to take the inverse and evaluate it at g of x, which is x cubed. So in the inverse function, I have the cube root of x, and for x, I'm going to replace it with x cubed. Well, what happens with when you take the cube root of an x cubed? Well, the cube root and the cube cancel, and you're left with x. So these two steps right here are very important, because the key here is showing that the following pairs of equations are inverses. And now stating it, we would say that g evaluated at g inverse of x equals g inverse of g of x equals x. Okay? And then finally, for this set, g of x equals x squared, the inverse of x, or inverse of g of x equals the square root of x. I want us to show that those are inverses for the x's that are greater than 0. Okay, so here we go. How do we do that? Evaluate the g function at the inverse. And the inverse, or the g function, is x squared. So what am I going to put in for x is the square root of x. When what do you get when you cancel or simplify the square root of x to the second power? You get x. And then the second part to this is you're going to show where g inverse evaluated at g of x. So the inverse is the square root of x, and we'll put x squared. And then the square root of x squared leaves us with x. So g evaluated at the inverse of g equals the inverse of g evaluated at g, both equals x. So those are the relationships, the key relationships and characteristics of inverses, and it all has to do with symmetry with respect to y equals x, the mom and daddy line. All right, so now let's kind of look at this from another type of perspective, one like you would see on an ACT or on an AP kind of question. We're going to assume that f is a one-to-one function, okay? And by saying that, we're saying that not only is f a function, but its inverse is also a function. So if we have if we know that f of 3 is 2, and we're wanting to find, f inverse of 2, well, we don't have any kind of equation to actually find it. Well, do we really need one? And we don't, because what's the relationship between the points of a function and its inverse? Well, if you think of this as a point, the x value is 3 and the y value is 2, what's the relationship between the x and y values of inverses? Well, the x and y values are switched. So f of 3 equals 2. Notice that for the inverse, the y value of the original is the x value. So f inverse of 2 must equal 3. So this is your x and y for the original. This is your x and y for the inverse. So your x's and y's are switched. Okay, same thing here. What about if f inverse of -4 is -1? Find f of -1. Okay, as an ordered pair for the inverse, -4, -1, then f of -1 would equal, -1 would equal -4. So it's just The x value of one is the y value for the other. Okay, so if f inverse of 3 equals a half, what is f of 1/2? Well, f of 1/2 is equal to 3. All right. Can we do the same type of thing with a table of values? So if I want to find f inverse of 2, this table of information is for f. But how do we use the f information to find f inverse of 2? Well, if 2 is the x value for the inverse, then 2 is the y value for the original. So the y value of the original is 2 for this point here. So therefore, f inverse of 2 is equal to -3. Okay? So maybe if it helps, remember, think of these two things. If you need to, think of these as ordered pairs. And 3, 3. So the x value of the inverse will be the y value of the original. So that would be -3. Okay? So f inverse of 2, if 2 is the x value of the inverse, you're looking for the y value of the original to be 2, which is here, so f inverse of 2 is -3. Okay? So this would be 2, -3, if that helps. Okay, what about f inverse of 0? Okay, this is f inverse. So if this is the x value for the inverse, I'm wanting to identify where 0 is the y value of the original. So in the y value of the original is here. So what is f inverse of 0? The answer is 3. Okay, so the key is knowing the relationship, that the relationship for inverses has to do with symmetry with respect to y equals x, and the fact that there's symmetry with respect to y equals x means that the an xy point for one will be the yx point for the other. Basically, your x and y values are flipped. Okay? All right, so this concludes the video for lesson 3.